Hello everybody, welcome to use xINTERPDF program. In this video, I will show you how to install and run the program. In order to install the program, you need to first download Anaconda. So you go to the download page of Anaconda, and currently xINTERPDF supports Mac OS and Linux. So you go to, if you're using Mac OS, you go to Python 2.7 version. It has a graphical installer. If you're using Linux, you can download Python 2.7 version and choosing 64-bit installer. And I have already installed the Anaconda. So first thing is to invoke a terminal like this. And let's check the conda version by type conda-v. So I'm using conda 4.5.4. And in order to install xINTERPDF, first of all, let's see what channel we have. So we type conda config --get channels. And you can see that I have diffpy query shcy channel. So if you don't see diffpy channel, you just type conda config --add channels diffpy. What it says that diffpy already in the channels. Okay, once you have a diffpy channel added, in order to install xINTERPDF, just type conda create -c -n xINTERPDF, then hit enter, and the conda will automatically search the necessary packages for xINTERPDF. Just keep in mind that there is an instruction about how to install the program in the GitHub page here. So it has a step-by-step instruction about what command to type and how to install the program. Okay, actually here you can see it has already founded the packages. You see you have xINTERPDF 0.1.0 version as Python 2.7, and it has all these dependent packages, dependencies, and just hit yes, proceed. So it starts to install all the necessary packages. It should take a while. Let's see. Okay. It seems it has installed the program. It gives you some hint. Basically, in order to start xINTERPDF, you need to type source activate xINTERPDF. And you can see there's a little parenthesis around xINTERPDF, which means you start the virtual environment for that. And once you start the virtual environment, then you type xINTERPDF to start the program. Okay, the program is there. It has a main interface that basically gives you some description about the program, and On the drop-down menu, it has XINTERPDF, which has crystalline amorphous ASD, and PDF fit. It has PDF fit and breakdown of fit. And it also have a utility tab, which has linear combination, and a PCA. I have prepared some examples here, which are for the demonstration of all these functionalities. Let's go over them one by one. First is XINTERPDF. Let's try this crystalline functionalities. Okay, so it says it is a study of intermolecular contribution via subtracting PDF of single molecule from the total PDF. We just follow the step. The step one is load structures and data. So load molecular structure. So we go to example 1. Molecular structure is in the form of XYZ. So open it and load crystal structure. That is mannitol zip file. Open. Load PDF data. That's the mannitol measured at 300K in the format of GeoVar. Open. Then in the step 2 is set parameters. We have two tabs, the molecular parameters. We just expand the SOMOS. You can see it automatically detects there are hydrogen, carbon, and oxygen in mannitol, and it is assigned the default UISO value of 0.005 angstrom square, and the occupancy is 0.1. And for the calculator, it has the by PDF calculator, and you can also select PDF calculator. For now, we use the by PDF calculator. And for the crystal parameters, we do the same thing. We just expand the SOMOS, and it has default assigned values. And atomic density, you can type in any number, or you can just leave it there by after we clicked visualization. We make the plot. You can see the program automatically figures out the atomic density for the crystalline form. So shown here is the interface for plotting the intermolecular PDF. The top panel actually shows the experiment, that's in black. That's experiment total PDF. And the PDF for the molecule, that's a calculation in the red for the molecule. And for the crystal, that's in the blue. That's a calculated result as well. At the bottom, in the bottom panel, you can see the green curve is the theoretical intermolecular PDF. That is crystal PDF minus the molecular PDF. And the magenta curve is experiment, which is experiment the total PDF minus the simulated the PDF for the single molecule. You can see they have fairly good agreement in the lower region. Of course, you can zoom in. There's a crosshair here. You can zoom in to look into the interesting region around 2.7. That is where the hydrogen bond should be. So our experimental PDF, by using the default value, is around 2.73, which is very close to the 2.72 theoretical value. Of course, you can fine-tune the parameters here. When you click this, you have the option to change the parameters for the molecule parameters, crystal parameters, and experimental ones. So for the molecular ones, you can drag the scale bar. Take a look at the red curve in the top. That is the molecule. So hydrogen bond doesn't change too much because scattering contribution is small. Let's change the carbon here. You can see, oh, it changed quite a lot. You can reset all to bring it to the default value. And for the crystal parameters, you can drag the scale bar. You can just type a number here. let's say 0.05 for the carbon UISO. That is in the blue curve. So let's see what happens to the blue curve. Oh, it just dramatically smeared out. And actually you can see that if you use a large UISO, you can see the higher region actually broaden out, which agree with experiment, and the lower region is, all the sharp peaks are gone. So actually you can see for the organic materials, you need two different UISOs to explain different regions. And for the experiment, there's nothing much to change. There is an overall scale factor, basically just first of all, let's reset default, and let's give it a scale factor of 2. You can see the black curve overshoots. And keep in mind, for the PDF GetX2, the scale factor for the your PDF should be close, very, very close to 1. But for other programs, the scale factor might be arbitrary, so you also have this option to change the scale factor. Of course, you can clear the plot, make the plot, and you can also save the plot. Let's give it a name, say XINTERPDF, save it, and we go to the folder, experimental 1, XINTERPDF. Actually, you can see there is a little description in the beginning. It says here are the raw data for the plotting the curve. You have chosen to use the BiPDF calculator for the molecule, PDF calculator for crystal, and you have also scaled the measured PDF by a factor of 1, which means we didn't scale it. That's the default value. And you see different data here, and it says from left to right, the data correspond to R, that's the radial distance, M, that's molecule, that's simulated PDF for the molecule, C is the crystalline, so the simulated PDF for the crystalline, E is the experimental PDF, and this column is C minus M, that is theoretical XINTERPDF. The last column is E minus M, that is experimental XINTERPDF. Okay, so that's for the XINTERPDF. As you can see, it also has Amorphous. It has a similar interface, except that in the step 1, you can only load in a single molecule structure. And for the ASD, you can load in 2 different molecule structures and also the PDF data. It has a similar interface to the crystalline case. Okay, so that's for the XINTERPDF. And the second one is the PDF fit to the organic crystalline PDF. So let's get started with that. You can see it has this interface. Let's load some structure first. First, the molecule structure. Let's go to the example 2. Let's load in MEF and ZIP file and the PDF data here. And you can see in the step 2, it has all these parameters here. Well, the QDEM and QBroad, those are the instrument parameters that should be fixed at the values you calibrate using the standard sample. So let's use these default values here. And there's also UISO for the intra, UISO intra, inter, and Qmin and Qmax. That is for calculate the single molecule PDF. And the example here is mefenamic acid, which has a P1 structure. So it has different ABC, alpha, beta, gamma. So in that case, you need 6 different constraints here. Basically means all these 6 parameters can vary. And there's a scale bar here. That's the overall scale, global scale bar. And there's also zoom factor here, which basically has option to isotropically expand or shrink the molecules. So the PDF can be shift to the left or to the right a little bit. And there's also 3 delta parameters here, which is used to explain the R-dependent peak width. And also you notice there is a check mark here. Actually, you can check it to fix the parameters. If you uncheck it, you just let it vary in the fit. In the step 3, select optimizers. First of all, you set a range to fit, let's say 1 to 20 in our case. Our step is 0.01, that's typical. And there's a bunch of optimizer. Let's use list squares as default. And then pretty much we can just start the fit, run the fit. And you can see in the console, the parameters are updated in the real time. Okay, so it seems it's close to finish. It's still running a bit there. And yes, the final result. Okay, it's there. So the RW is about, that's the quality of fit parameter, is about a 0.178. That's good enough. And actually, if you go to the experimental 2 folder, you can see 10:49 p.m. That's just right now. So it generates 5 files, and it has a crystal.cif file. That's for the final refine the crystal structure. And there are 2 different molecule structures in XYZ format. It has a fit, which contains all the raw data for the plotting, and also have a result file, which has extension res. Click that. It has the same thing that is printed to the console, and all the parameters here, the final one. Okay, that's basically the how to run a fit. And there's a functionality that is called breakdown of the fit. So we have a total fit. We have just run a fit, and then actually we can break down what is what does intra PDF look like, what does inter PDF look like. So we can actually load the structure. We just load the result, all this file generated from the previous fit. Let's load this intra, and mole structure is this, crystal structure is that, fit data is this guy, fit result is this. And step 2, we set different Qmax. 24 is a good one, so let's click max a plot. Yeah, you see it has break down the total fit into different parts. You can see this guy is top left corner is intra PDF calculated, and this calculate crystal PDF and calculate molecule PDF. and the difference of both gives you the calculate xINTERPDF. A summation of the red and this magenta curve gives you a total calculated PDF, which is in this yellow or golden curve, and the experimental PDF is shown at the bottom. You can see they agree with each other quite well. Okay, that's that. And for the xINTERPDF, there are two different utilities. One is a linear combination. Let's click that. This is the interface. Basically, it says we try to find the scale factors that minimize difference or maximize the similarities between PDF A, B, C, or AB, and a target PDF D. So let's look at some examples I have prepared in the experimental 4 folder. You can see 5 files, and so MA100, that's the melt-quenched atazanavir, that is an amorphous drug, and RC100, that's 100% copovidone, that is a polymer, and there's also A25, C25, 75, 50-50, and 75-25. Those 3 guys are the ASD, which basically is you can think about it as a physical mixture of the drug and the polymer, and we know the nominal concentration of that, 25, 50, 75 for different drug concentration. Let's see, can we just can retrieve that number by using the linear regression. So let's load the data. Let's load the PDF1, that is the end member, that should be a pure drug, for example. And the PDF2, that should be pure polymer. Let's load this guy. And we don't have a PDF3, so let's load the target PDF. That is, let's try this 50-50 first. We can, in step 2, we set different range. Let's set 30, and then in step 3, just run the fit. And you can see that it gives a scale factor of 0.47, which is close, which is good. We use an optimizer that is least square. Let's change to Pearson and run the fit again. It gives roughly the same number, and there is also a least absolute deviation as a standard. Run the fit again. Well, it's roughly about the same. Okay, we can load a different target. Let's load 25 this time, and then run the fit. Yeah, it gives a value about 0.247. That's close. Let's load the third one. That's 75. Run the fit. It gives a 75.84. So that's pretty good. And well, you can change the range. 15 angstrom, 76. That makes sense because all the information is in the first 15 angstroms, and then beyond the 15 angstrom, that's virtually 0. And you can change the steps as well. It's 0.02. You cannot see the difference. Let's see, 0.1. Yeah, it becomes rugged, and say 1. Yeah, that's that's too much. Okay, there is a final functionality from xINTERPDF. Under Utilities, there is a PCA. Okay, so that's the interface for the PCA. So the principal component analysis is a machine learning technique, is unsupervised machine learning technique. It is often used to reduce the dimensionality of your data, and it also performs the clustering, basically find the similarities between different data or different sample without any prior knowledge. let's see how it works for our PDF. So in the step 1, just load a series of PDF. Let's click that. Let's go to the example folder 5. So I have 4 different PDF data collected at 300 Kelvin. One is GSF, it's Grisoformin, indomethacin, mannitol, and mefenamic acid. Let's load all of them. And let's use 1 to 40 is our step 0.01. Okay, in the step 2, just hit make the plot. Okay, and you can see the 4 PDF curves are represented by the dots here. And 2 of them are clustered together. One is indomethacin, the other is Grisoformin. As you can see, these 2 guys has a similar size in terms of the molecule size and the molecular weight are quite similar. So that's perhaps the reason they are clustered together. And in this score plot, you can see the first 2 principal components are plotted, and x-axis is principal component 1, and the second axis is principal component 2, and in the parentheses that is the percentage of the principal component, and which is better plotted, demonstrated in this scree plot. You can see actually it has 3 different principal components, and the first 2 has more than 80% of importance, while the PC3 is not that important. So actually we can save the plot, and save it and give it a name, PCA. Then we can open it. It's here. It has a little bit description here, the raw data. So here are the raw data for the scores and scree plots. So the first column corresponds to the file name, of course. The second column corresponds to explained variance for the scree plot. That is the number here. You see 0.65, that is 65% for the PC1. And PC2 is about 20 something, that is a 223, 0.237 here. And third PC is about 11%. And from third to the end are the 4 principal component values. It has different values. The first column is PC1, PC2, PC3, and the PC1 and the PC2 numbers are used to generate this score plot. And when you have a lot of samples, you might see the legends is too big. You can actually change the legend marker size to a smaller one. Let's say 4. Let's clear the plot and make the plot again. You can see the legend and also the scatterer becomes much smaller. Then you can put more dots onto the plot. Okay, so that's the final things you can do with xINTERPDF. That's it. That's the first version of xINTERPDF. I'm still working on it. Hopefully I can include more functionalities in the coming months. And once again, thanks for using xINTERPDF. Thank you.